Je fais mes travaux au laboratoire de génie civil et génie mécanique. Et donc, j'ai le plaisir de gérer cette session, d'animer cette session autour des matériaux naturels. Donc, nous aurons 6 présentations. Et donc, effectivement, un rappel des consignes. Vous avez 10 à 12 minutes de présentation qui seront suivies par 3 à 5 minutes de questions. Donc, vous pouvez poser vos questions dans le chat et je les relayerai. Et donc, le temps des présentations, on éteint nos caméras et moi, je rallumerai la mienne au bout d'environ 10 minutes. Comme ça, vous saurez qu'il vous restera 2 minutes de présentation. Donc, je cède la parole à Monsieur Hassan Fardoun qui va nous parler de the monitoring the effect of age and drying on fracture behavior of earth concrete.
Juste, excusez-moi, juste 12 minutes.
Oui, c'est ça.
Oui.
C'est entre 10 et 12 minutes et du coup, après, il y a 3 à 5 minutes de questions.
Merci. Donc, je me lance.
C'est parti.
This is Hassan Fardoun, a PhD student at the University of Bordeaux. This work concerns the monitoring of effect of age and drying on the fracture behavior of earth concrete. L'écran ne bouge pas. Maintenant. We will be going through a basic outline starting from introduction into conclusion. Starting by introduction, concrete is a construction material that poses disadvantages. It's responsible for the release of 7% of greenhouse gases and the depletion of natural resources. Accordingly, eco-friendly approaches are being proposed. They aim mainly to curb the use of concrete or at least to reduce its harmful effect. The construction material proposed in this study is earth concrete prepared with recycled sand. Earth construction has been in service for thousands of years. It has taken different forms such as adobe, rammed earth, compressed earth, and wattle and daub. It's of low cost, limits energy consumptions, and controls room temperature. On the other side, recycled sand mostly comes from the construction and demolition waste that accounts for more than 1/3 of all waste generated in Europe. The limitations of landfills, resource depletion, and CO2 emissions are behind the use of CDW in construction materials. Recycled sand is of high water absorption capacity than natural sand. What would be the effect of replacement of natural sand by recycled sand? In addition, what's the effect of clay content? Different variables such as clay and cement accounts for strength development and fracture behavior. How would earth concrete behave with curing age? Both earth materials and recycled sand are sensitive to shrinkage and drying. How would this affect the compressive strength and fracture behavior of earth concrete? Our study assessment will be by means of acoustic emission and digital image correlation techniques. Starting by the materials, the earth materials in this study are clay and sand. A non-swelling kaolinite clay was used. The water absorption of natural sand and recycled sand respectively are 1% and 14.6%. The water content of each component was determined. Here we can see the particle size distribution of each component. 30% of clay was mixed with 70% of natural sand. In addition, 20, 30, and 40% of clay were mixed with the relative amount of recycled sand accordingly to form the following clay sand mixtures. Each mixture was stabilized by 9% of cement of dry components. In addition, water was added. And finally, the road to earth concrete is done by making this mixture pourable. This was done using superplasticizer Tempo 10. Mixed design, generally speaking, when recycled aggregate are used, a pre-saturation test took place. It was decided to pre-saturate the recycled sand at 50, 80, and 100% saturation degree. When recycled sand is included, the term water is replaced by the term effective water, which is equal to the total water minus the water required for the recycled sand and the water required for clay. For this preliminary test, the recycled sand with 70%, the mixture with 70% recycled sand was considered. Here we can see all components are the same except when the saturation degree changes from 50 to 80 to 100. Accordingly, the water effective changes. It's aimed from this preliminary test to assess the impact of saturation degree on the mechanical properties of earth concrete compression and flexion at 28 days. The slight increase in slump values as the saturation degree increases was accompanied by a very slight decrease in the mechanical properties. As long as there was insignificant differences, our choice was rather governed by the slump value, aiming for a slump value more than 7 centimeters. The 80% saturated degree was considered. Here we can see the mixed design of the 4 mixtures. The increase in clay content was accompanied by increase in the water effective to achieve similar workabilities among all mixtures. Experimental procedure, 10 centimeter cubes were casted to get demolded after 3 days and cured for 14, 28 at 90 days at a relative humidity of 90% and relative humidity of 50%. For the compression test, electromechanical machine of loading capacity 100 kilonewton was considered. For the acoustic emission is the study of elastic wave generated by a material when it's exposed to external loads. Such waves are of friction and cracking sources. When the wave is initiated, it travels throughout the material to be captured by piezoelectric sensor. The latter transforms the wave into electrical signal to be studied or analyzed by the examiner. In this study, we used 8 piezoelectric sensors, and the detection threshold was kept at 33 decibel to avoid any environmental noise. For the digital image correlation, software VIC-2D was considered. Results: effect of recycled sand. The compressive strength decreases as the recycled sand replaces the natural sand. Why? Because indeed more water was required to compensate the loss in workability due to the high water absorption of recycled sand. Thus, the increase in the initial water content is responsible for the loss in strength. Similarly, the fraction energy decreases. These 2 figures shows the correlation of stress and acoustic emission activity of both mixtures. Both mixtures showed 4 phases. Phase 1 is of low acoustic emission activity due to the contact between the loading plate and the specimen. Phase 2 is of limited diffuse damage, limited acoustic emission activity due to the diffuse damage. A sharp increase we can see in phase 3, indicating the formation of macro cracks, to decrease after that in phase 4, reflecting the stable propagation of cracks. Still in the correlation of stress and acoustic emission activity, the higher strength of natural sand mixture was reflected by higher acoustic emission hits. Here we can see the acoustic emission energy, acoustic emission peak frequency of both mixtures. The acoustic emission activities were distributed at the same peak frequencies. However, the mixture of recycled sand was of lower acoustic emission energy, indicating a weaker material. Finally, with the digital image correlation, the lower strength, lower fraction energy, lower acoustic emission hits, and lower acoustic emission energy was reflected by a higher degree of damage at peak of the recycled sand mixture. Regarding the effect of clay content, the compressive strength decreases with clay content. Similarly, as in the recycled sand, more clay content requires more water. The mixture with the lowest clay content, RS2080, evidence the highest fraction energy. The acoustic emission energy decreases with clay content, indicating a weaker material with clay content. Regarding the correlation of stress and acoustic emission hits, the mixture with highest strength revealed highest acoustic emission hits. And finally, with the digital image correlation, the RS2080 showed the least degree of damage at peak. Regarding the curing of age, these 3 figures shows the stress strain, the correlation of stress and acoustic emission activity of the natural sand mixtures at different curing age. We can see that before the peak, the acoustic emission activity decreases with age, indicating a less rate of damage due to the increase in the strength. This aspect was reflected according to the digital image correlation with the decrease of the degree of damage at peak. Take, for example, the RS2080 as an example. We can see how the degree of damage decreases with age. Still in the effect of curing age, these figures shows the stress correlation of stress and acoustic emission activity at 28 days and at 90 days. We can see that in the post-peak region, a gradual increase in acoustic emission activities was recorded at 28 days. However, a sudden increase in the at 90 days. This shows that this sudden increase reflects a more brittle behavior of curing with curing age. Finally, with the effect of drying, this figure shows the evolution of the first figure shows the evolution of compressive strength of each mixture at 14, 28, at 90 days curing at both curing conditions. Basically, all mixture exhibited increase as a result of drying. Basically, as a result of shrinkage, clay particles got closer to each other and more in direct contact, enhancing friction and leading to strength development. This justifies the lowest increase in strength as a result of drying in RS 2080, the lowest clay content, and this justifies the highest increase in strength in the RS 4060 mixture. Regarding the recycled sand, we can see that the increase in the recycled sand mixture due to drying is less than that in the natural sand mixture. This indicates that more shrinkage-induced cracking were formed in the recycled sand mixture, curbing the effect of suction effect. At 90 days, at RH 50%, we can see that the natural sand mixture, the compressive strength, still increases. However, those for recycled sand mixture decreases. This reflects the vulnerability of recycled sand to drying. The second mixture shows the effect of fraction energy. The fraction energy decreases with prolonged drying. Basically, the least decrease was in the mixture with highest clay content. The last slide here, the correlation of stress and distribution of hits of one of the mixtures, RS 2080, at RH equal 90% and 50% at 28 days. We can see that in the part before the peak, increase in the acoustic emission indicates premature damage due to the shrinkage-induced cracking. In the post-peak part, we can see a gradual increase in the wet specimens. However, for the specimens subjected to drying, we can see a sudden increase of the acoustic emission activity, indicating a more brittle behavior with drying. The first aspect was reflected by an increase or by an evolution of the strain fields in the pre-peak phase of the dried specimens. In addition, this evolution of strain fields was much remarkable in the recycled sand mixture, again, reflecting the vulnerability of recycled sand to drying at peak and at the post-peak. The specimens subjected to drying were of higher degree of damage. Here we can see, for example, the natural sand mixture at 50% post-peak, how the degree of damage is higher. Finally, a conclusion, the compressive strength decreases when recycled sand replaces natural sand. This was reflected by lower acoustic emission activity and higher degree of damage. The lower acoustic emission activity with clay content is due to lower strength and lower heterogeneity of clay. The acoustic emission activity showed lower rate of damage in the pre-peak phase with curing age due to the increase in strength. Recycled sand is vulnerable to drying, a less domination of suction effect in RS mixtures with prolonged drying. The AA activity reflected the premature damage caused by the shrinkage-induced cracking. Earth concrete is more brittle with curing age. Thank you very much.
Merci. Alors,
c'est bon avec le temps?
Parfait. Pile poil 10 minutes. Est-ce qu'il y a des questions? J'en ai pas vu dans le chat pour l'instant. Alors, je suis en même temps... Alors, est-ce qu'on peut poser les questions en français?
Mais doucement, s'il vous plaît.
Doucement, d'accord. Alors, donc, est-ce qu'il y a des questions dans la salle ou dans l'assistance? Alors, moi, en fait, je ne suis pas du tout une spécialiste du recyclage des matériaux et en fait, j'avais une question toute simple en fait au début. C'était le sable recyclé. Est-ce qu'il faut le pré-traiter avant de l'utiliser?
The treatment we didn't do any treatment. Yes, some of them do a treatment, but basically now for the recycled sand is mainly laboratory studies. It's not yet have been used in the at the field. For the moment, it's just limited for the field for the laboratory studies.
Okay.
Still the high water absorption of it. So if you need to do, like, for example, any treatment, the main problem of it is now the water absorption. So we are not going now to the next level of treatment. Is this?
Ok. Et du coup, si on ne fait pas de traitement spécifique, le fait qu'on diminue les résistances mécaniques qui sont plus faibles avec le sable recyclé qu'avec le sable
avec
classique.
le natural, compared to natural sand, yes.
Yeah. Do you have an idea from of the
lower decrease?
Yeah.
En fait, due to the high water absorption of, basically we have two things. Due to the high water absorption of the recycled sand, we added more water, right?
Okay.
Let's say we used the recycled sand without any pre-saturation, and we have like 30% of natural sand, and we have 30% of recycled sand. If we put here 3 liters of water and here 3 liters of water, the recycled sand mixture is not going to absorb the recycled sand mixture is going to absorb all the water. So it's not going to be workable such as the natural sand. So the increase in the initial water content leads to the decrease in strength. And another thing, the recycled sand are full of cracks and full